Hello, welcome to e-learning session. So for the session 3 we are planning to discuss about the ARM architecture. In the previous session already we have discussed about the ARM hardware components as well as the embedded system software components we have discussed, and in this session let us look into the ARM core and find out the exact architecture of the ARM and ARM in general ARM family architecture. Say inside the ARM core, say as we have discussed earlier, we have the ARM bus, so ARM high performance bus, and then ARM peripheral bus connecting the core and the different peripheral components and memory components. So just inside, as we have seen here, we have a DMA port, we have the on-chip memory, and we have the ARM peripheral bus and ARM high performance bus, and then connecting to the core link and the different say UART and clock devices and so on. And this is the exact the ARM core we have. And another in detail let us see the different various components of specific example of ARM processor. So here I have a vectored interrupt controller here, and this is the exact ARM core what we have, and ARM core is connected to the ARM say the bus high performance bus which is making use of the AMBA protocol, the AMBA AHB bus we have, and connected to the high speed controllers or which requires the high speed throughput. So we have vectored interrupt controller we have connected to the AHB, and we have another say bridge now connecting to the peripheral bus. So yesterday we said about APB, now here we have instead of APB, so it is shown as a VPB, that is a VLSI peripheral bus is shown here, and to this peripheral bus the different peripheral components are connected, like say for example UART, real time clock, the watch time dog, and then watchdog timer and USB ports and so on are connected. On this side I have external interrupt say controllers, D2A converter and A2D converter and so on. So these are the various components, peripheral components connected to the peripheral bus are called as VPB in this case, and on the other side I have the ARM local bus connecting to the internal SRAM and flash memory controller and so on. The SRAM can be a 8-bit or 16-bit or 32-bit say word byte size is 8-bit or 16-bit configurations, or 8 KB, 16 KB or 32 KB configuration supported by the SRAM. So these are the various components we have. So this is how the various components that are found inside the processor core. Now let us take at say the ARM processor. Basically it is a simple design comprising of an architecture, load store architecture. As we said earlier, load store architecture is nothing but a general register based architecture. That means to say only the load instruction and the store instruction will have the access to the memory, and all the remaining say the processing instructions like the arithmetic and logical instructions do expect the data only from the registers. So that is what the general load store architecture, and ARM processor being a RISC processor, it adopts the load store architecture. An ARM processor is a 32-bit processor, which I mean to say like it comprises of a 32-bit data bus, and it uses 3 different addressing modes. So with this I just say that the ARM processor adopts a simple design, right? And the ARM processor since it uses a RISC architecture, we say that it is a simple architecture, and it has a simple instruction set, that is a reduced instruction set, and being say the ARM processor supporting the 32-bit instruction and 16-bit instruction, the code density also is an important criteria here. Our code density improves. So with that, so the ARM processor has these main important characteristic features, and with these characteristic features definitely the ARM processor is small in size and it's a low power consumption say processor core. Now let us look at how the data is transferred between the memory and the processor. Say I have the processor on this side, and we have the memory configuration and how the data is transferred from the memory to the processor. This let me call it as the address bus, and this let me call it as the data bus. Okay. Now as I have shown here, the data bus from the data bus, the ARM processor receives the data, and this data whatever that we have shown here, it is information received from the memory. That is what received from the memory, and say the received information, if it is an operand, it just goes this side. If it is an instruction, the instruction part or the code part, so since it is to be decoded, it moves to a unit called as the instruction decoder. So this is the path followed by the instruction, and it enters into the circuit called as the instruction decoder, where exactly the operand, that is opcode that is present in the instruction, will be decoded so as to involve the necessary circuits for the completion of the execution of the instruction, and that decoding takes place in this unit. And if the information received from the memory through the data bus, if it is an operand, it just goes to the register file via a sign extend unit or via a sign extending circuit. So to do that, it just passes and then enters into the register file. So this circuit sign extend is necessary only when the data received, if it is a half word data, that is 16-bit data, or if it is a word data, byte data, that means a 8-bit data. So if at all I receive 8-bit data or a 16-bit data, then before it is getting stored into the respective register in the register file, the sign is to be extended if the number is a signed number. In which case, suppose let me take an example. If the byte received is 1000 and 0010, let me take this as the first example data, and next another example data, let me call 0110 1100. Let me take these two examples. So in which case, if this is the byte that is received from the data bus, then in that case the sign extension unit will appropriately put in the remaining 3 bytes position, in the remaining 3 byte positions. So it will copy whatever the last bit here will be copied in the subsequent say byte also. This is what the sign extension circuit does. If the last bit, the D7 bit of the byte received, if it is 0, in that case this remaining say the bytes, remaining bytes, so will copy 000 000 and so on. So it copies only zeros into the subsequent 3 bytes. So I have shown only say 1 byte here, another half I have shown, but the same thing is copied into the remaining 3 bytes. 1 byte I have shown here. So total word size is 4 bytes, that is 32-bit data. So being 32-bit data, the data received, if it is 8-bit data, then the sign extension circuit or sign extend unit will appropriately pad zeros or ones into the remaining higher byte positions. That is what done by this circuit. And the register file is actually a register file actually comprises of a set of registers. Each register is of 32-bit wide. That is what we have. And the data enters the processor core through the data bus, and data may be an instruction to execute or an operand data item, as I have just considered earlier. So let us further see the memory. Because the data is received from the memory, the instruction or data is received from the memory to the processor, and say after that the instruction decoding and the register file we discussed now, the type of the memory that is used here, say based on the organization of the memory or the architecture of the memory. So we can classify the memory architecture as the von Neumann architecture or Harvard architecture. So earlier we have discussed about the memory hierarchy. That means to say between the processor and the memory, we have various levels of the memory we have. Like for example, we have the cache memory, we have the different levels of the cache, we have the main memory, we have the secondary memory, we have hierarchy of the memory. Now since I have the memory classified as von Neumann architecture or Harvard architecture, now the difference between these two is only how the instruction and the data are fed from the memory. That is what the difference matters here. Let me take the example here. Say I will take the example that the processor and memory, that means to say the processor will receive the data and the instruction from a common unified memory. So in which case I have the memory, and the memory I will give the address here and I will receive the information. The information could be either data or instruction. That means to say in this model we find that the data and instruction reside in a common memory, a single memory or a monolithic memory, whatever that we call, or sometimes we call as unified memory, unified cache or unified memory I call. So from the unified memory, that means to say wherein both instruction and data reside together. So the data and instruction are fed. So this is what the first memory architecture I have, that is called as von Neumann architecture. Now the next I have, the second category is the Harvard architecture. In the case of Harvard architecture, what we do is like we exactly split the memory vertically. I split. That means to say I will just consider the processor here. I will consider the processor here, and the processor is connected. The processor is connected to the memory. So I have the memory split here, and I have another piece of memory here. So I will get I will pass the address here, and I will get the instruction. Let me call this as the instruction memory, and this as the data memory. So the address and the data, this is the address and this is the data, right? Information, instruction, let me say. And here the address is sent to the memory and the data is received or data is stored. So this is what I have. This is exactly like the instruction and memory, sorry, instruction and data are residing in separate memory units. So I have instruction memory and I have data memory. These two are in the separate memory units. With Harvard architecture, the benefit I get is like while I am accessing the instruction, so simultaneously the data also can be accessed. That means to say from one side I will be getting the data and from the other side I will be getting the instruction. That means to say the instruction and data can be accessed from two different memory units simultaneously, or a kind of parallel activity is happening here. So therefore the Harvard architecture always supports for a higher throughput, or the speed of the memory access could be overall could be better. I can just represent the same thing in a different way. So like connecting either on two sides we can show, or I can just simply represent the processor here, and we have separate memory units here, separate memory units. So this is the bus have right. So we can have like this, or the subsequent level of the memory could be monolithic also. In other words, like in the hierarchy of the memory, the cache is split vertically. Let me call this as the on-chip cache. So this is the on-chip memory, but the memory is unified, and then the cache is split. So this I'll just say that it is a combination are the mix of von Neumann and Harvard, right? Because one level is say split, split vertically, and the other level I have not split. So this, the different levels talks about the hierarchy, whereas in each level I have either the memory split vertically or entire memory we have split horizontally, right? This is what the memory architecture is, right? The difference we said, von Neumann is simple, but Harvard is say provides a better access rate, right? That's what we have. Since von Neumann is provides a unified memory, naturally the instruction and data should go together, right? Suppose with this type of say organization, if at all I have, in which case the data stored here is instruction and data together resides here, whereas if it is instruction, the data accessed, if it is an instruction, so it should go through this, and if it is a data, it should go through this. So this is how I need to just bifurcate and then forward the data towards the processor, right? It's very simple. It's very simple. So this is one important aspect of the memory architecture. Then coming to again, if the memory is used, if it is multi-byte word, if it is a multi-byte word, that means to say the memory, the processor is say like 16-bit processor or 32-bit processor, in which case each word will have multiple bytes. Let me select a memory of 32 say bit word or 4 byte was what is used in the case of ARM, right? So let me select the memory. So these are the different words I have. So each word comprises of 4 bytes, right? Each word comprises of the 4 bytes, right? So this could be like byte number 0 having the data D0 to D7, and byte number 1 say having D8 to D15, and so on. And this is byte number 2 and byte number 3 and so on, right? And this forms the word 0 word, and this is another word, second word, and so on. So this is how a 32-bit memory or a 4-byte word memory looks like. Now, when I spread the data into this kind of memory, that is a 4-byte memory, so in which case the lower byte of the memory, byte of the data, whether it sits on this side or it sits on this side. Based on this, we have 2 types of memory called as the Little Indian organization or Big Indian organization. That's what as we have shown here, Little Indian or Big Indian. ARM can be set up to access its data in either Little or Big Indian format. But before that, let me just make the clear difference between what we have between the Little Indian and Big Indian. So as it is indicated here, the Little Indian, the least significant byte of a word is stored in bits 0 to 7. That means I select the first word in that the LSB of the data, the least significant byte of the data do sit here. The next byte will sit here. That means to say the byte the data will spread from the right end towards the left, that is from D0 to D31, the data spreads D0 to D31. So least significant byte will sit here, the next higher significant byte here, and the most significant byte will sit here. This is what a Little Indian memory looks like. Whereas in the case of Big Indian, the least significant byte of the memory data, least significant byte of the data will occupy the B3, and the next higher byte will occupy B2, and the reverse way it goes. This is what a Big Indian. So Big Indian starts spreading or starts saving the data in the memory starting from the most significant byte of the word, whereas in such a way that the least significant byte of the data will sit from the bit number 24 to bit number 31, and so on. So this is what the difference we find. So Little Indian we have and the big endian we have. So of course, like when the word saved, I mean like data saved, if it is a word length, it doesn't matter to us whether I follow the little endian or big endian. It is internal say responsibility of the bus and the controller to provide the data in whatever the way it just stores there. It becomes very easy. Whereas if at all I start say accessing only half word, that means say 2 bytes from this, then the question comes is like whether it is a little endian or big endian, because I need to reconstruct the data after I take out from the memory. That means say I take out half byte, half word from here. So whether when I take half word, so which byte is the least significant byte and which byte is the most significant byte. That is decided by the type of endianness followed in the memory store. Another important point here is like say when we talk about the little endian or big endian, so if the word that is to be accessed, a word is to be accessed, especially in the ARM, what is followed is like each new word will start from a new word. Each word will be stored from a new word, or it is boundary aligned. Word is boundary aligned. So therefore that means to say the word address will be always a number which is divisible by 4. That is what. That means to say if at all a word sits in the memory, it always sits from a new word, occupying the complete this say 0 word, byte number 0, byte number 1, 2, 3. So sits there, or byte number 4, 5, 6, 7 is used. That means to say a word will not be split and then it will not occupy say either half word here and then a half word here. So that way it will not occupy, or ARM will not support for such configuration. So the word will sit completely, or word is sits with word boundary aligned. That is what the important thing you should remember. So I have taken an example here, so showing the example data as the data 44 is the least significant byte of the word, and the next I have 33, 22 and 11. So this is what the data I have here, and this selected data, if it goes to the little endian, how the different bytes will occupy. Say 44 being the least significant byte of the data will sit at the least significant byte address of the word. It sits here, whereas on the other side you find that the 44 sits here, this side, right? 44 sits here in the case of big endian. So that is what the difference you find here between the little endian and the big endian, right? Now let us further go into the processor core. So already we discussed about the sign extend unit, the instruction decoder unit we discussed, and the data was received from this side, and we assumed for this model of ARM discussion, I assumed that the data or the bus is this which connects to the memory, and the information received from the memory could be data, in which case it goes through the sign extend and then goes to the register file. If it is an operand, if it is an instruction, I assume that it goes this side. That means to say I am receiving both data and the instruction from the same bus I am receiving. That means to say this particular model what I have shown here is corresponding to the von Neumann architecture. Of course, let me make a mention that the ARM, we have different versions of the ARM core we have. So we have the ARM core which are adopting the von Neumann architecture, and there are some say ARM processor cores which adopts or which uses the Harvard architecture. So both the type of memory architectures are used. So at the concluding slide, I'll just show some of the example ARM processors which adopts the Harvard architecture, and the remaining which adopts the von Neumann architecture. I'll just show in the conclusion slide. I'll just show. So now we came up to the register file, and we said that register file is a 32-bit, say each register is a 32-bit, and I have say some set of registers that are present in the register file. Let me just take up the exact registers count and the different types of registers. We have general purpose and special purpose registers. In the coming slides I will just take up. Now let me just move ahead. Say here I have a barrel shifter, and on this side I have a MAC, MAC called as MAC, right. So let me just discuss about what is this barrel shifter. The name say specifies here or gives a clue that it is a shifter, but the shifter I called it as a barrel shifter. Say earlier we have seen in the case of 8086 processor that it has registers on which we can perform the shift operations or rotate operations. We have shift right, shift left, rotate and so on we have. But here in the case of the ARM processor, I am capable of performing the similar type of operations on the registers, but apart from that I have a special circuit called as the barrel shifter. The barrel shifter, that means to say the ALU gets input directly from the register that I have shown it as operand 1 here, and the second operand will be fed to the ALU through a barrel shifter. A barrel shifter actually say is a unit which will make some pre-processing of the data before the data is fed into the ALU. That is what the barrel shifter does. So that means it makes a shift either right or left. I can shift a number and then I can feed it to the ALU. That means I will just get from the register here. I have a register here, and through the register I will get a barrel shifter. Whatever that I get the content of Rn, I will just give it to the barrel shifter, and from the barrel shifter I am just giving it to the ALU. That means the number used here or the data that is received into the barrel shifter can be forwarded as it is to the ALU input, or the data can be shifted either right or left. I can shift and then do it. So this shifting either right or left, I am just calling it as a pre-processing. So I can pre-process the data and then give it to the ALU. So if at all I make a pre-process and give it to the ALU, so the time required for processing the instruction reduces, or say for example in one instruction I will be performing one addition I can perform, and similarly I can perform a multiplication and then I can forward it to the ALU. That means in one instruction I can complete both a multiplication as well as an addition I can complete as a single atomic instruction. I can just do that. So that is what the beauty of the ARM processor is, or this is one of the most powerful instruction that we find in the ARM processors. And coming back again, say this operand 2 which I am giving here, it just gives along with the instruction I can specify a shift value. A shift value I can specify. So the shift value is specified using a 5-bit unsigned integer. When I say like 5-bit, the maximum value I can use is like 32. So each register is 32-bit wide. So a 5-bit unsigned integer could be used as immediate value along with the instruction to specify how many bit positions the shift is to be done this way or this way. That can be specified using a 5-bit unsigned integer, right? And then this is specified in bottom byte of another register, of course, like say this is used, or the barrel shifter is used for multiplication by a constant. So that is what we just do here. And if at all it specifies an immediate operand, it could be 8-bit number with a range of 0 to 255, and it allows the increased range of 0 to 32-bit and contains to be loaded directly into the register. That is what we have. So just to say that barrel shifter does a magic, it does, or it does a pre-processing and then feeds it to the ALU, right? Now let us see further, right? So we just came up to the sign extend unit register file and the barrel shifter. Fine. On this side I have a unit called as MAC. So this multiply and accumulate. So then say I have a mathematical series I have. So I need to say keep multiplying the values, the two numbers whichever that is fed here through the A and B. Say I call this as the input A and this as input B for the ALU circuit, and the input A and B are fed to the multiplication and multiply and accumulate circuit, and this multiply and accumulate circuit will multiply the two numbers, and it keeps accumulating the values. So for example, I just say like x into y plus x say the values whatever that I get here through the AB. Let me just select that say AB itself. So let me say like A into B plus say A square plus B square, sorry 2A into B, something like that. I have a series, and this accumulation, this multiplication and added into an accumulator. An accumulator A into B I will perform, I add it here. The next set of data I will give and I will add it here. So let me say I can just use two register values, multiply them and then keep accumulating, right, keep accumulating. So this kind of things I can just do it. So for this we have, of course, like specialized instructions are available in the ARM instruction set, and such instruction set will make the programmer's job more simple, and the accumulation becomes quite easy. Otherwise I should do this multiplication using one instruction and addition using another instruction, rather than using two separate instructions and then putting in a loop. I can just put only one instruction, that is multiply and accumulate, so in a loop, and then I can just do it. So that is what the advantage of using a separate circuitry called as the multiply and accumulate circuit. Again, this is again another strong feature of the ARM processor, right? And whatever the result obtained here or received, so this is again stored back, and accumulated value is obtained here received, and the input data, the two operands and the previously accumulated data, that is what received here, and all these things are these two are multiplied and added with the previously accumulated value, and the result goes back into the same register. So that is what the circuitry we have, or this is the exact the data path for this unit, right? And this side I got a number directly from the register into the ALU through one of the input, that is the input A, and input B I can pre-process and then give it to the second input of the ALU, that is I call it as the input B, right? Or this side I have shown it as N I have shown. So these two are say the computation is performed on these two input operands, and the result is obtained here, and the result can be put into the back into the register file, right? So that is what we have. And on this side I have the address register, because sometimes it is necessary to compute the say the branch instruction addresses, and the address registers are used here. So I have a incrementer in normal event, say incrementer is there, and the address is incremented. That means after fetching every instruction, the address after fetching every instruction, the address is to be incremented so as to point to the next instruction address, or I need to keep updating the program counter, for which a circuit is necessary, and that is done by this circuitry, right? And the address is obtained here, and say this is how the ARM say core looks like. So on this side I have shown the memory, on this side I have shown the processor core, and say what we have shown here is the processor core gives the address to the memory. On this side I receive the instruction, or I receive the data, and the results are put back into the memory. Of course, like the results are put back into the memory, or the data is received from the memory using only the load instruction or store instruction only. So that is what that is why we call the ARM as a load store architecture. Now coming to the core again back, say let me just say identify the circuits by the type of the task that is done by the circuitry, right? And whatever this side I have here is responsible for generating the address of the next instruction, say forward the address, give a control signal so as to receive the instruction from the data bus, right? So therefore let me call this circuit is responsible for fetching or getting the instruction into the processor core for the purpose of instruction decoding, and whatever the operand necessary is again the address is forwarded and the data is received here. For example, if it is a instruction is a load instruction, the decoded instruction is a load instruction, the address is to be specified and the address location is to be accessed and the operand is to be received and then sent to the register file. If it is a store instruction, again I need to forward the content of the register to the memory. So for all the other I will just get here, and this is the circuit responsible for fetching the instruction, right. I call this as fetch circuit, and this side I have the data received or the instruction received. So instruction is getting decoded here. I call this circuit or the components that are responsible for the instruction decoding, I will just call it as the decode circuit. And this part, the central part, I just call it as the circuit or unit responsible for the execution of the instruction. Whatever the opcodes that is included in the instruction, that instruction is to be executed. So this becomes the execute circuit. That means to say, I just divided the whole core into 3 different category of circuits: the fetch circuit, the decode circuit and execute circuit. So this is how I just say shown. Let me just show here. So I will just receive the instruction. The instruction is getting say fetched and it gets decoded and the last is execute. Though I have shown this side, but the diagram shows in a different way, as in a form. Say this of course like shows only the data flow model, but here I have shown the consecutive actions, stage wise actions that are taken while instruction gets executed. First instruction is to be obtained from the memory, for which we perform the fetch operation. The instruction is to be decoded before actually executing the instruction. Then at the last stage or the final stage, I call it as the execute. So this is what the data flow model is shown here, and whatever that I have shown there is the instruction flow model, right. So using this say the second part, whatever that I have shown here, let me just rewrite this clearly. Say we have the fetch, right, decode and execute. So if I consider these as the 3 different say sequential tasks that is done for the instruction execution, so I just consider that when the first instruction of the program is fetched, say I will just fetch the first instruction of the program, and soon after it is fetched, I just perform the decode of the first instruction. When the first instruction getting decoded, the second instruction of the program can be fetched, provided these circuits are independent of each other. This is most important, right. So the fetch circuit should be independent of the decode circuit. A decode circuit should be independent of the execute circuit. If these circuits are made independent, then definitely when the first instruction is getting executed here, the second instruction will be under the decode phase, and the third instruction of my program will be getting fetched from the memory. And since all these 3 are happening in the time overlap fashion, that means to say simultaneously all these are happening. The first instruction is executed, the second instruction is getting decoded, and the third instruction is getting fetched. Or let me take some other example. Suppose like say the 5th instruction is getting executed, the 6th instruction of the program will be decoded, and 7th will be in the pipeline. Or considering all these activities, I can call this activity of time overlap fashion of execution, or let me call it as the execution which is done following an assembly chain, right. So you find that say the place where the assembly is done, so you find the assembly section, say the first person will put a resistor on the board, he will pass it on to the second person will put a capacitor and he will pass it on to the third. So this is how the assembly of a circuit or electronic device happens, right. Similar way, I have just realized a similar mechanism or similar method of execution of the instruction, starting from getting the instruction into the core, right, getting the instruction into the core, and then decoding the instruction, and finally the action that is required for the completion of the instruction. All these are done in assembly chain fashion. So this type of activity we call it as the instruction execution using a pipeline activity. That means say the activity will flow in a pipeline, right, will flow in a pipe similar to that. So this is what the instruction is getting executed. Pipeline is quite say a mature technology. So this is not a very new, right, it's a very say mature technology. We find the way back say many processors are having the pipeline, or in other words now I can say that all the processors do make use of some kind of parallel processing in the case of the instruction execution, and the instruction path or the instruction flow, if it is similar to this, then we call it as the pipeline. Say here I have taken an example program of assembly program I have selected. I have an instruction, nth instruction is add, the n plus 1 instruction, n plus 1 is subtract instruction, and the n plus 2 is the compare instruction. So here on the other side I have shown that in the specific cycle number, say let me say that starting from this point, if I say like so I will just I am just considering, so in the specific cycle the first instruction gets or the instruction they add, say add, subtract, compare I have. So when the add is getting executed here, the subtract instruction is in the decode stage and the compare instruction is in the fetch stage. That means first the instruction is say inserted, fetched, and then it gets decoded in the next cycle, right. In the first cycle the add instruction here, whatever that we have considered, is fetched. The next cycle the instruction add instruction is decoded, and in the last cycle the add instruction is executed, or it is execution is completed, addition is performed, and then the results are written back. So this each phase, let me call this fetch as one stage of the pipeline, this as the second stage of the pipeline, and this as the last stage of the pipeline what I have considered for this example, right. So I can call this pipeline as a pipeline of 3 stages. So in each stage a specific activity is done, and each stage is independent of the remaining stages. Now let me just select the example of ARM7 processor, ARM7 processor. So ARM7 processor adopts a 3-stage pipeline. So this corresponds to the instruction fetch, the first stage. The second stage is nothing but the decode stage. So in the decode stage, if it is a 32-bit normal instruction, the normal instruction is decoded, and the register select is done in order to fetch the subsequently the operand, right. That is what done here. If the instruction fetched is a 16-bit instruction, or what we call it as the thumb instruction, so the thumb instruction gets decompressed, and then the instruction gets decoded. Let me say the decode circuit is a fixed circuit which decodes a 32-bit instruction. Now in this the early stage of the second stage of the pipeline, early phase of the early phase of the second stage, if the instruction fetched is a thumb instruction, then naturally decompress is done, and then in the later half of the stage or later half of the cycle, the instruction it gets decoded. That is what put together, this is the second phase of the pipeline or second stage of the pipeline. We have the decode stage, and the last stage is the register read. So register read, I have just considered the execute as a cycle which has different say sections. We have the register read, the operands access, operands are to be prepared and then forwarded or made available to the processing circuit. So therefore the operand access is nothing but the operands are made available to the processing unit. That is what the register read does. And then shift, this is actually the shift which is done, the second operand passes through the barrel shifter. So this is what the second second section of the execute, and the processing is done here. And the last is the register write. The results are put back into the register. Let me select an example. Let me say that an example like let me select an example like say add R0 comma R1 comma R1 comma shift left 2, R0 comma R1 comma R1 comma shift left 2. That means to say I have specified the operands R0 R1 and the R1 being the second operand, the R1 operand I will just shift, I will pass through the barrel shifter, and here I am shifting it by 2. That means to say the shift by 2 is taken care by this fellow, this part of the or this circuit, that is nothing but the barrel shifter. The barrel shifter will come into picture here, and whatever the input given to the barrel shifter, so it performs the shift operation and then sends that to the ALU. That is what done here, right? And R0 is the first operand, say it goes. So this is how I can just perform, right? And this is the register, right? Whatever the results that are say computed are to be put back to the register, right? Results computed. So here I perform that shift operation is done here, and the add is done here. The R0 goes directly, R1 comes through this, and then result is obtained, and the result is put back into the register file R0. So that is what I am doing. So an interesting factor. So this is again when I have a pipeline, naturally the performance or the execution speed will improve, right? So by using a 3-stage pipeline, the speed up what I expect is 3x, right? But due to some reasons or the theoretical speed up of 3x will not be achieved always. Rather we achieve a speed up nearer to or greater than 1.5 for most of the applications. The reasons for not achieving the speed up of 3x is not under the purview of the microprocessor or the particular say syllabi that is set here. So let us say that using such pipeline, it is possible to say speed up the performance of the execution by a specific time. Okay, so theoretically 3 stage if I use 3x I should get. Say ARM uses ARM7 uses 3-stage pipeline. Say for example, I can further divide this into subsequent smaller say subtasks and then make the pipeline a longer pipeline. It is possible. So there are some pipeline ARM processors which do make use of 5-stage pipeline. Say overall the instruction execution has only this much actions only, but only thing is like I just reserve say the register access and shift operation as one cycle and one stage, and ALU and register write as the next stage, by just appropriately splitting each stage into the 2 or multiple stages, I can have realize a deeper pipeline. I can realize. So by having a deeper pipeline, always I tend to get a better performance. But of course, like sometimes we also have some disadvantages by having a deep pipeline also. But however, restricting ourselves to the ARM processor has all the ARM process do use the pipeline activity for the instruction execution, and there are some ARM processors which makes use of the 5 3-stage pipeline, like similar to the ARM7, and then we have some ARM processors examples which do make use of 5-stage and so on. So let me just say that the ARM family versions, the pipeline depth, ARM7 uses 3-stage pipeline, 9 uses 5-stage pipeline, ARM10 uses 6-stage, ARM11 uses 8-stage. As the stages increases, I am expected to get more and more performance benefit, right? And one more point, I was just telling that when we discussed about the memory organization, I said the ARM will make use of the ARM family. There are some example processors which make use of the von Neumann architecture, and there are some example processors, ARM processors which make use of Harvard architecture. If you see like ARM7, it makes use of von Neumann architecture, whereas the ARM9, 10, 11 are the advanced versions when compared to the ARM7. So they do make use of the Harvard memory organization. When the Harvard memory organization is used, definitely we know that the data will be fed from one bus and the instruction is fed from the other bus. So therefore we can get a kind of parallel activity. So therefore the performance of the processor will improve. So that is the reason why we make use of Harvard architecture. Of course, like when I am achieving a better performance or when I am using a higher level of the parallel activity, naturally the cost will be higher. So with this I think we have discussed today in the session, we have discussed about the ARM architecture, what all the various units that are present inside the ARM processor we have discussed, and we have also looked at the data flow model of the ARM processor we have looked at, and we have also looked at the instruction path, and finally we concluded by introducing the pipelines that are used in the ARM processors and the different ARM processors comparison with respect to the pipeline stages used, and then the type of memory organization used, we have just compared them, and then so these are the things what we have discussed in the today's session.